Hello, my name is Luka Biedebach. I'm a computer scientist, and I will give you an introduction into machine learning and digital healthcare. I'm sure all of you have heard this buzzword somewhere, but today we're going to actually find out what machine learning is about. So we're going to start by looking at the fundamentals of machine learning, and then we will have a real-life data set to explore, and I will give you a crash course in Python. Here we can see our schedule for today, and let's dive right in with the first topic. Introduction to machine learning. Our goals of today are to find out what is machine learning, what are the most common machine learning models. We're going to look at two more simple examples, so you'll be able to understand after the session how the k-nearest neighbors model works and how decision trees work. And then we will go through a step-by-step guide to your first machine learning model. So there's this fixed process we need to follow when creating a machine learning model, and we will go through each and every step of them. The first one is looking into the data, pre-processing the data, creating a train test split, and afterwards learning how to properly evaluate a machine learning model. When we hear machine learning, most of us might think of supervised machine learning models. That's the part right here, where we have data and we're trying to attach a label to a data record. But actually, machine learning is much broader. So we also have unsupervised machine learning, where we're trying to segment data into groups, or we reduce the dimensionality of data. And another form of machine learning is reinforcement learning, where we feed the data bit by bit with new information. And because our time here is limited and we're trying just to get a little insight into the big field of machine learning, I'm going to talk today mainly about classification. But please keep in mind that other forms of machine learning exist. Let's start at the beginning. Generally, if we are asking ourselves what machine learning does, it is about learning or teaching a machine to do tasks that usually humans do. So there are some tasks that we as humans, we just know the answer to a question. But it's kind of difficult to explain why we know that answer. So if we look at this picture, everyone in this room will know that this is a dog. And if we look at this picture, everyone here will for sure know that this is a cat. But if I ask you to explain to me why you came to this decision, why we see on the dog on the left and the cat on the right, it gets already a bit complicated. You can say, the dog has 2 ears and it has shorter fur and it has a different anatomy of a cat. But it's really difficult to explain exactly how you formed that opinion in your head. And the reason for that is that throughout your life, you saw hundreds and maybe thousands of cats and dogs. You remembered how they looked like, and you created an internal model of a cat and an internal model of a dog in your head. And if you see another picture of a cat, then you're just immediately know that it's a cat based on this model of a cat that you have. And what we're trying to do here is teaching a machine to also create this model of something internally. So when a machine learning model is approached with a new image, then the machine learning model also internally knows how to decide. So how can we teach a machine how to build this model in its head? It's kind of similar than you growing up as a child. You look at thousands and 10,000s and maybe 100,000 of pictures of dogs, and we tell them every time, this is a picture of a dog, this is a picture of something else than a dog, this is a picture of a dog. And by repeating this step many, many times, we build this internal model. That doesn't mean that the machine is always right. If we confront them with a picture that is not a dog, and not a cat, it might still be confused what it is. But the more we train the model, the better it will get. And we will look later at different strategies, how to train the model, how this works. So looking at those pictures is called model training, and applying this knowledge to an unknown object is called model testing. But in order to understand machine learning, let's go back a couple of dozens of years, back into a time where machine learning was not a buzzword yet. Back in classic programming, we as the user would give instructions to a computer, and these instructions would be formulated as rules. For example, this rule could help us to differentiate between a cat and a dog. If the animal has 2 ears and has a weight of more than 10 kilo, then it's probably a dog. Then the computer would take in these rules, and every time it's confronted with a new animal, would check those different conditions and come up with a result. However, this is quite limited. So we would need a lot of rules to cover those special cases, and the results might not be very accurate. And how is machine learning? Let's see the comparison. So in machine learning, we don't provide rules, but instead we provide examples. And by providing those examples, the machine derives its own model. So let's look at a formal definition. We give the examples, or we can also refer to that as the data, and we give the class labels, and then the machine derives the model. And what we get back is not only the result, but also a function that can classify these unseen records. So we input a record and we output a class label. That might seem a little bit abstract, so let's look at 2 examples within healthcare to understand this concept. So the first example that we look at is a data set on blood transfusion. So it is a database from a center in Taiwan that does blood donations, and it has data on 748 people. And so the data set we're looking at is a blood transfusion data set. It's from a blood donation database in Taiwan, and it has information about 748 different people who donated blood in the past. And it has information about these people, and then it has also information whether they donated on a certain donation day. And the goal of this data set is to predict whether a person will donate blood based on information from the past. So if we now take this example and go back to our formal definition, the input into the model is the data on the donators, and the output is the function whether a person will donate blood or whether they won't. And let's look at this data. So this is how the data looks like. We have different information about the blood donors. So we have the recency, when did they donate the last time. So in the first row, which would be the first person, it is 2 months ago. How many times did they donate in the past? So we have a frequency, so that this person has donated already 50 times in his life. And then we have a monetary value. So that means how much money they got in the past for donations. And then the time in months means here the number of months since the first time they donated. And the column on the right, this will be our target variable. So this is the information we're trying to predict with the machine learning model. And this says whether he or she has donated blood in March 2007. So if we see a 1, it means that the person has donated blood in March 2007. And if we see a 0, it means the person did not donate blood in March 2007. So when we're thinking back of this separation between the data and the class label, It means the data is the information we input into the model. So this would be, for example, the image of a dog, and the class label is the information we give about this image or about this data. So this information in this case is, did the person donate blood or not? But in the example of the dog, this would be the information, is this a dog or is this a cat? And this is what we call the target variable. So what happens now? We need to derive a model from this data we're seeing. And for simplification, I just took the first 5 participants here. But keep in mind that in the whole data set, it's more than 700, which is approximately, which is the amount we need to train a machine learning model. This would not work with 5 rows. And in general, we can say the more data, the better the prediction will be in the end. So the first step here is to derive a model from this data. And then, once we created this internal model, we can make predictions whether the person did donate blood or not. So in the prediction step, we would only know the information about the person, but we don't know yet whether the person did donate blood or not. So now we need our model to make the predictions. And that is called classification. So our model will now classify those examples that the model has not seen before. And this way, it would either assign a 1 or a 0 to the row, depending whether it's more likely that this person donated blood or not. And then we can verify those predictions with the true label. So we can compare if the label of the predicted value and of the truth value is the same. Let's look at a second example. I know everyone here will be maybe more interested in this one because this is about sleep stages. So if you listen carefully to the lectures before, you have seen the setup for sure, the polysomnography. So we have all the different channels giving us information about different parts of the body. And in this data set, we're going to look at EEG. Now we go back to comparing this to our formal definition. So the examples that we input into the model will be sequences of EEG. And what we get out of it will be a function that can classify EEG into a sleep stage. So the input are PSG signals and the output will be a sleep stage. And now this is a typical representation of EEG signals. So we have here one example of light sleep. So this is just a short epoch, deep sleep and REM sleep, just so you see how we're going to look at it from now on. But if we have this data imported into Python, this will be a time series of numbers. So depending on the sampling frequency, it can be thousands of numbers in one array, which represent just one 30-second epoch of sleep EEG. So we're looking at quite complex data here. So I'm using both examples, the blood donation and the sleep EEG, because the blood donation is quite easy to comprehend because it's only tabular data. But this sleep example is a bit more complex because it's time series data, but I wanted to take it in just to give our sleep experts here a sleep example. Yes, and then on the left side, so the EEG, that is the data, and then the label, the sleep stage, is the target variable or the class label. And now the same thing as before, we show the model hundreds and thousands of epochs of EEG, and we always assign the label, is it which sleep stage it is. And from this information, we can derive a model and use this model to classify sleep stages. So again, this would be the classification step. And just looking at the EEG, our model would predict whether it's most likely to be deep sleep, light sleep, or awake. And then we can check these labels with the expert label. And here we already can see the model is not always right. We always have a overall accuracy of the model, which tells us how accurate the predictions are, and we can actually calculate that. So here 2 of 3 cases are correct. Model accuracy is 66%. This is something we use to evaluate the model, but we will dive into this later in more detail and find out exactly how to evaluate machine learning models. So now we saw some examples. Now I always use the term, this is where the model will train, but there are different methods of training a machine learning model. We will look at those two today, the k-nearest neighbor and the decision tree, because those two are easiest to understand. There are many, many more different methods, but yeah, we will focus on these two for now. So the k-nearest neighbors. This is a model that makes a prediction based on the label of the records that are most similar to the one that we're looking for. So these most similar ones can be referred to as the neighbors. And we use those neighbors to learn values of unknown points. And the k here in the name is the number of neighbors we're looking at. So let's do an example of a k that would be 3. So we could also call this now the 3 nearest neighbors. And on the right side, we see a map of Iceland. And we see the weather in different locations Iceland. For everyone who has been in Iceland, it can be very different from location to location. But yeah, this is just a toy example. So let's say we're searching for the weather in this place, which is probably around Selfoss. And in order to find out the weather at this place, which is right now unknown to us, we would find the places that are closest to Selfoss. So this would be probably like Vik and Reykjavik and Akranes. And then we would calculate, for example, the medium temperature of those 3. Or we would, in this case, think that since it rains in all 3 cities around this area, it will probably also rain in Selfoss. And then we would assign the label rain to this position. Another example, this is probably Egilsstaðir. We don't know the weather there, but we do know the weather in Djúpivogur and maybe in Mývatn and what's up there, Bakkagerði. And since 2 of those locations show rain and 1 of them shows sun, we would probably guess that it's also rainy in Egilsstaðir. However, we also take the distance to those neighboring points into account. So if we would weight the vote of Djúpivogur higher because it's closer to Egilsstaðir, then we might predict the label that it's sunny in Egilsstaðir. But this depends on how the k-nearest neighbor is configured. So which k is best? That's a question that I cannot give any general answer to. So in this case, we could look at the map and see that those 3 cities around are a good approximation, but you can never know beforehand which k is the best. So what we usually do in machine learning, if we have an unknown parameter, this is like the like a little adjustment we can do to the model. So k would be our parameter. And if we do have an unknown parameter like k, then what we do is test different variations. So we would test the model with k equals 2 and k equals 3, k equals 4, and every time check what are the best results we're getting out of this, and then in the end choose the k that delivered the highest accuracy of model predictions. So this is called hyperparameter tuning. So tuning those adjustments to make the best possible model. We will not dive into all the details on hyperparameter tuning in this session, but it's a super interesting topic and I highly recommend reading up on it. So as I said, there are different variants. Take the majority vote or weight according to distance. Great. Here's another example, which is a bit more complex than this easy map. So this is a plot of our blood donors. So on the x-axis, we have the months since the first donation. And on the x-axis, we have the months since the most recent donation. And we can already see kind of a pattern that people who recently donated and recently started donating overall have more orange dots, and orange here means the one, so a person who did donate on March 2007, so think back of the example we had before. And now we will put some unknown points in this plot. So here's one. And we don't know about this person, whether they donated in March 2007 or not. And in order to find out or to make a prediction, we will now search for the 3 closest neighbors, which are those 3 top points. And since 2 of them are blue, we will predict that this donor is also blue, so did also not donate at this date. Another example here for this donor. The 3 closest points are those, and 2 of them are orange. That's why we would predict that this person is also orange, so did also donate blood on this date. Yes, and of course this is a prediction, so we don't know if these people actually donated or did not donate, but that's something that we will evaluate later. And now a bit more complex example, the sleep stages again. So on the left side we see the sleep stages we already know, and on the right side we have an unknown sleep stage, so we have just the EEG, but we don't know which sleep stage it is. So in this example of k nearest neighbor, we would here in this easy example now set k to 1, which means we will look for the most similar EEG in all of these 5, and we will decide that this one is most similar to the unknown one, and then make the prediction that this is also awake. So this seems quite simple now, but keep in mind that this is a simplified example. So in real life, again, we would have thousands of EEGs, and in real life, we also need to come up with different approaches of comparing the similarity between different EEG sequences. But in general, this is how it would work. And another form of training a model is creating an internal decision tree. So we present the model, again with the old example, with pictures of thousands of cats and dogs and dinosaurs and whales and worms, and then every time we give the model the label, is this a cat or is it a dog? And then based on this information, the model creates this tree. And let's first look at how the tree is set up. So it is starting always in the top. And let's imagine we're seeing a picture of a dog. Then we would ask ourselves the question, does it have feet? And yes, it has. So we would move to the left branch of the tree and approach another splitting attribute. So we would ask ourselves another question: does it live in a house? And yes, the dog lives in a house, so we would move further along to the left side of the tree. Reaching the next splitting attribute would be, does it say meow? And no, our dog does not say meow, so we move to the right side of the decision tree. And then we arrive at the terminal node. So this is our decision. The animal we're searching for is a dog. And the one advantage of this model is that it's really easy to understand as a human. So we can always follow those branches and then understand why the machine learning model made a certain decision. But I think the main question is now, how do we create this tree? So how does the model come up with those branches and splitting attributes? And for this, we're going to look at split criteria. So the tree searches for the best possible split criteria. What is that? The way to find the best splitting attribute is to look at the distribution of the data at every node. So we're trying to measure the purity. And a common measure of node purity is the Gini index or Gini coefficient. And it was defined by Corrado Gini in 1912. And back in the days, he was looking at the distribution of wealth across the country. So a Gini index of 1 would mean that one person in the country owns everything. And a Gini index of 0 would mean that every person in the country has an equal share of the wealth. And here below you can see the formula of the Gini index. So the bracket means the relative frequency of class J at node T. So if we have 10 people and 2 different classes, then the relative frequency of class J at node T would be the number of one class in comparison to the number of people overall. And then we take this times itself and then take the sum of all the classes, of all the nodes, and then we do 1 minus this sum. But let's look at an example to understand this better. So in the box, you see all of the instances at a certain node. So here we have 6 different points. And then we have 2 classes. And there is only 1 point of the class 0, which is blue. So the formula would be 1 minus 1 divided by 6. So here 1 is the number of instances in class 0 and 6 the total number of points, squared minus 5 divided by 6, which is the number of instances in the other class, squared. And this would result in a Gini index of 0.278. Another example where the Gini index is a bit higher. So here it is more balanced. We have 3 instances of class number 1 and 3 instances of class number 2. So you can see how the formula would be filled out below. And we end up with a Gini index of 0.5. And now, keeping this Gini index in mind, this tree was actually trained on the blood transfusion dataset. And here the model tried to find the best splitting criteria among those 4 columns that you can still see on the left side. So our first splitting attribute is the recency, whether the person has donated blood in the last 6.5 months or not. And then we just move along the branches of the tree to end up in the decision node. And then the color of this node indicates whether the person is predicted to donate or not. What we can learn about this model is that we also have parameters here. So one parameter would be, for example, which kind of purity measurement we choose. So are we choosing the Gini index or something else? Another parameter is the maximum depth of the tree. So how many nodes should we go along until we end up at the decision node? So the more nodes we choose, the more complex the tree is. And here we need to take care not to make the tree too simple or too complex. But these are all things that we need to test out when creating the models and then evaluating them. So this quite simple decision tree, for example, has an accuracy of 78.5%. So again, this is the recency, the first splitting attribute. And if we have this example here of one donor for which we don't know yet if he's a donor or not, we would look at the frequency that is reported in his data. So it's 4 months, so it's smaller than 6.5 months. Then we would go along the tree like this. So I'm just showing you now how a decision would be made within this tree. Then we would look at the recency again and follow now the left side of the tree. Then we would check the number of months since the first donation, which is 16. And this is why we would follow along this side of the branch, and then we would end up in our terminal node, which is the final decision. And now we will look again at a simplified version of sleep staging. So if we have this EEG sequence above the head of the robot, then a decision tree could be trained by checking for sub-elements of that sequence. So we could check, does it have this part of the EEG in there, or does it have this part? And based on that, we can find out that it might be REM sleep, and that would be the prediction. So we're always looking at which branch we go down to the terminal node. Yes, and this was the first part of the lecture. Now we will look at the step-to-step guide that I promised in the beginning. And yeah, this is what we call the data mining process. You can see that there are 5 steps for now. And the start of this process is the data itself. And the first step of the process is the data selection. So this is something that happened even before I introduced you to the data. So yeah, selecting which information we need in order to create knowledge in the end. So if you follow along all of these steps, we will end up at knowledge, which is in our case having successfully taught a model how to make human decisions. Then the second step of the data mining process is the pre-processing. So at this step, we will, let's say, clean the data, because most of the data we as machine learning users, let's say, get is quite messy, and it needs to be in a certain shape for the machine learning model to work. So actually, most of the time in this whole process is spent just in the first 2 steps, in selecting and pre-processing the data. Because once it's cleaned up and ready, those further steps are usually less complex than the pre-processing itself. Yes, so here it becomes a bit difficult, and you will need some experience with machine learning models to know what kind of pre-processing steps you need for which kind of data set and for what type of classifier, so what kind of machine learning model. Because different machine learning models have different demands, because they are, let's say, sensitive to certain things. And also different types of data sets have completely different needs in the pre-processing. So pre-processing this blood donation data set is a whole different story than pre-processing the EEG data. Now I will give you examples mainly for the classic input to machine learning models, the tabular data, like we have in the blood donation data set. So common steps here are handling missing values and remove measurement errors. So, for example, if we have this data set below, it's already quite clean, but missing values would be, for example, if we just don't know certain information about a person. So let's say we don't know when they donated for the last time, and then this might be empty or there might be a 0. And we then have to think about how to handle this. Are we throwing away the whole row? Or are we filling it up with a 0? Or are we filling it up with an average value? And that again depends on which model we're using, and also what the data means. So we need to really understand the data. So for example, in the recency, if we have a missing value there and fill it with a 0, that means that the person donated this month. However, that would not be the truth, right? So we really need to think about the data when we do the data cleaning. What does it mean? And then measurement errors, that's a whole topic for itself. Because the first problem will be finding measurement errors, because sometimes we have extreme values that might be just extreme values, but sometimes we have extreme values that are wrong values, maybe typos or errors in measurement devices. And sometimes we have measurement errors that are not even extreme values, so they're even harder to spot. So if you look here in the first row, there is one person who has donated blood apparently 50 times. And this seems quite high to me, considering that he first donated blood 98 months ago. And then we need to think, is this realistic? Is it maybe a measurement error? Maybe it should be 5 times and someone actually typed a 0. So here sometimes we have to go row by row, but optimally we would find automated ways also to identify those measurement errors and to remove them. But yeah, we don't have time to cover all areas of machine learning here, but it's also a very interesting research area, this outlier detection and removal. Something else that's important for some machine learning models, not for all of them, is encoding categorical data. So here our data is it's only numerical values. So we have numbers in the columns. But for example, our target variable, that is a text field, right? So this is a category, and we have 2 categories, and they are donated or did not donate. And a machine learning model cannot, or some machine learning models cannot handle this. So we need to transform these values into 0s and 1s. So here we would assign the number 1 to donated and the 0 to did not donate. Because the 1 is usually the positive number, or let's say a number that we are looking for, the interesting one. And the same could happen for categories within the data field. So for example, if we had the gender in there, and there would be male and female and diverse, then we could categorize it as 1, 2, or 3. Just turn the text into numbers. And the last thing here on the list is unify scales. I think I first need to explain why we need to do that. And that also depends a bit on the machine learning model. Because, for example, if you compare the similarity between points and you're taking multiple columns into account, and you're looking at the recency, which is a number that typically ranges, let's say, between 0 and 12. But then we have the monetary, so the number of the amount of money they got for donations in the past. That we can already see here ranges between 3,000 and 12,000. And the problem in many machine learning models is that the higher numbers kind of overshadow the smaller numbers, even though they might be equally important. So the recency is just as important in this model as the monetary value. However, it is 10,000 times higher than this one just in the scale. And that's why it could mess up the importance of these features in some models. So just to be sure that everything is correct, we usually bring all features to the same scale. So we scale them into a range between 0 and 1, or sometimes -1 and 1. And so the information they keep, they still keep the original information. We just, let's say, shrink it or extend it to be all on the same level. But again, I could have 3 lectures just on how to scale values correctly. But this is just for you to get an impression what we need to do. For more deep dive into these topics, I would recommend to look at more machine learning lectures. Okay, so the first 2 steps are done. Next step that is written down here is the transformation. What is meant by that? Here we are splitting data into a format that is usually the input for machine learning models. So you're probably wondering, why do we need to split the data set? The reason for that is that we want to keep a certain amount of the data for training the model. So these are the pictures that we show to the machine learning model, and it learns from them. But then we need to keep some of the data aside to validate the model in the end. So it's very important not to mix the data we use for the training and the data we use for testing. Because the cool thing about the machine learning model is that it can predict a label for data it has never seen before. But in order that this condition is fulfilled, we need to make sure that it has actually never seen this data before. So before we start the training, we need to split the data, best is doing this randomly, into separate sets. And typically we use around 80% for the training, and then we use around 10 to 20% of the data set for testing. And then if we're really serious about our machine learning model, we should keep also another set, which we call the validation set. So this will be left out even from the testing, because as I told you before, we often create a machine learning model, test it, and then we have to adjust some parameters, for example, rerun it, test it, and then maybe we change the preprocessing again, rerun it, test it, and this way we make our model better and better. But at some point we need to watch out that we don't optimize the model so much that it's only working on this specific data set. This would be called overfitting. And again, I can't go into too much detail on this. But in order to make sure that we're not overfitting a machine learning model to a certain data set, we keep out a validation set for the very end. When we run the final model and we say, okay, we're done here, the task is solved, then we test the validation set just to be sure that we're not overfitting. Okay, and this can then be 0 to 10% of the data set. Again, like now in our examples, in our coding example, we will not be this serious about it because we're, first of all, not doing a serious hyperparameter optimization. But just so you know, in real machine learning projects, we're keeping a validation set. Okay. And how do we split the data set? So I told you, like, the approximate number is around 80% for the training set, but this really depends on your personal preferences. But yeah, we would just, for example, here we have 100 participants, and then we would take 80% of these participants for training, 10 for testing, and 10 for validation. Yeah, and again, there's different approaches on how to do this. Should this be random? Should this be stratified? That's something I will show you in a few slides. Again, this is only a shallow insight into machine learning. So here, a little summary, divided into train and test set. If you don't have a lot of data and you feel like you can't afford of leaving out 20% just for the testing, then an alternative is called cross-validation. That means that you, let's say, a 10-fold cross-validation would divide the data into 10 folds and then always use 9 of them for training and 1 of them for testing, but then run the model 10 times. So each fold has been used for testing once and all the others have been used for training once. And then you can calculate the averages. But yeah, that's, again, more details than you maybe need at this point. But something that is important to know is that if your data set is imbalanced, it makes sense to make sure that each class is represented approximately equally in the train and the test set. And this is why we do a stratified train-test split. I have an example for that. So imagine from those 100 people, only 7 of them were donors, so only 7%. It would make absolute sense to have both donors in the train set and in the test set as well, because we need those donors to learn about both classes in the train set. So in the train set, the model needs to look at examples from donors and from not donors to understand the differences and to learn a model of both classes. But then also in the testing, we need to know how the model performs on donors and how it performs on not donors. So here we should make sure that there are enough donors in each set. So in the training set, test set, and validation set. And for that, we can use a stratified test split, which automatically matches the distribution of the classes from the training set with the distribution of the classes in the test set and the validation set. And now we go on up the ladder of the data mining process. The next stop is the data mining itself, so training the model. And I already showed you 2 models so far, the k nearest neighbor and the decision tree. But if you look at this map, there are many more. And even for an advanced machine learning programmer, it's not always natural to know which model is the best fit for your data set. So here we see some kind of decision map, which can help us to find out which is the right model for our data set. And I put the link there for you. So if you're ever in the situation, you can go on this website and follow this path to see which one is good for you. But in the end, often what we do is we do this process with multiple models, and then we compare their performance in the end. So maybe there is not the single right solution for your data set. It often makes sense just to test multiple ones that are suitable and then choose the best one. Good. And then we're almost at the end. The next step is the interpretation and evaluation. So if you remember this example from the blood donors, we predicted a label, is a person a donor or not? And then we also have the truth label. And what we're doing now is comparing the predicted label and the truth label. And what is very helpful to do this is putting all of this in a table. So a 2x2 table, and the columns indicate the predicted class and the rows indicate the true class. Based on this table, we calculate evaluation metrics afterwards. But let's first try to understand the different fields in the table. So the true negatives are the examples where we predicted a negative class and the negative class was correct. So in our case, the negative class is did not donate. So in this case, this person is someone who did not donate. And in our model, we also predicted that this person did not donate. So we did the correct prediction for the negative class. And then if we move one to the right, we have a false positive. So this means that we predicted that someone donated, but in reality, this person did not donate. So this is a false positive. So overall, a false prediction. Then if we go to the one on the bottom left, this would be a person who we said did not donate, but in reality, they did donate. So this is also a false prediction, and it's exactly the opposite of the other case. So in this case here, we said someone did not donate even though they did. And in the top one to the right, we said someone did donate even though they don't. So both of them are wrong, but they are wrong in different ways. And then the last one is our favorite one, where we say someone donated and they actually did. So you can see that the top left and the bottom right are the correct predictions, and the bottom left and the top right, those are the false predictions. And if we now look at the table above, we can try to place these examples. So here we can see that we predicted someone donated, and they actually did. So this would be down in the bottom right here. And then here we predicted that someone did not donate, and they really didn't donate. So this is a true negative in the top left. And then here we predicted that someone did not donate, but in reality they did. So this would be a false negative. And now maybe you can take a second to think about how the table of this one would look like. So this would be someone where we predicted that they did donate, but in reality they didn't. Okay, and let's get some numbers out of this table. Here on the left side, you can see the actual table from the decision tree that we trained earlier. So because we had around 700 people, we divided this in train and test set. So here we have around 140 for testing. And you can see in the squares which were correctly classified and which were not correctly classified. And the most common evaluation metric is how correct was the classification. That's our accuracy. So we take all correct predictions and divide this by all examples in the test set. So in this case, all of the all correct predictions are the ones in the upper left square, so the 105, plus the predictions in the lower right square, so the 16. Those are all correct predictions, and we divide those by all of the examples in the test set, so by the sum of all squares. And yeah, let's move on to the next evaluation metric, and those are twofold. They belong together, precision and recall, and they consider the number of examples in each class. So these are very useful for imbalanced data sets. Like in our case, our positive class is the one with fewer examples, in our case donated. So if we look at the precision, we're trying to find out how many classified donors were correctly classified. And then, so how precise was our prediction of donors? And then the recall would be, how many donors did we identify? So how many, this also kind of indicates how many did we miss, right? So we have this whole amount of donors, and then how many of the right ones did we pick? And these are usually quite opposite, because if we're trying to be more precise, it can happen that we lose some of the donors that we then do not identify. And then if we identify more of the donors, it can be that we lose some of our precision and have more false positives in there. So let's look at the numbers. Here, for the precision, we use the true positives divided by the true positives plus false positives. So here we take 16, so the bottom right, plus 16 plus divided by 16 plus 9. So we have precision of 0.64. And for the recall, we take the true positives and divide them by the number of true positives plus false negatives. So here it is 16 divided by 16 plus 20, which equals in a recall of 0.44. Okay. But most of the time when we do machine learning, we want to be both. We want to be precise, but we also want to identify as many positive examples as possible. So now I will introduce you to a very common metric in machine learning. It's the F1 score. And this is the harmonic mean between precision and recall. So for a high F1 score, we need both high precision and high recall. The formula is 2 times precision times recall divided by precision plus recall. And let's fill this in. So when we use the precision and the recall we calculated before, we just calculate 2 times the 0.64 times 0.44 divided by 0.64 plus 0.44. And the result is the F1 score. So this was the data mining process. This is, on a shallow level, all you need to know so far about machine learning, at least for our real-life data project and also for the Python crash course. So this was the machine learning process. We learned how to pre-process data, how to split the data, how to select a machine learning model, and finally how to evaluate the data. And in the next chapter of this lecture, we will learn how to turn all of this newly acquired knowledge about machine learning into actual Python code. So in our Python crash course, we will go through all of these steps again, but this time with real-life data and coding examples. So I'm very excited to test it out. I hope you are too. And thank you for this session.